sales endpoints, so cash registers, card swipers and whatnot. But more importantly, IBM provides service basically. So let's say you're Wells Fargo Bank or you're a huge bank, okay? So instead of having your own servers and whatnot, and you have to spend your own money to hire your own people to do it, you can subcontract that to IBM. You basically say, IBM, I can pay you this much money. Okay, I need 99.999% uptime with my servers. Make it happen. And IBM is going to make it happen. So IBM, I think historically, is very good at delivering what they promise. It's not cheap, okay, but they always deliver. So in the world of banking and also government agencies and whatnot, if you know the expense ahead of time and in return you're getting the guaranteed uptime, it's worth the money. It's worth every single penny. Because a downtime, can anyone imagine how much money Wells Fargo Bank will lose just with 1 or 2 hours of downtime? It's a huge amount of money. Okay, it's a huge amount of money. So the amount of money they pay IBM to maintain their servers, their services and whatnot, and also having the expertise when something goes wrong, that they can send an expert over to help fix problems, to these organizations, it's worth the price. Because you're basically trading something that is predictable for something that is unpredictable. So it's about risk management from these organizations' perspective. All right, so I'm gonna close this one, okay? And also I got one thing from the Design Hub. The Design Hub is going to do, I think, a lot of work with 3D modeling and Unity programming and VR programming. So if anyone is interested, you have time, over the summer, and you want to get a quote-unquote internship, paid or not, I do not know yet, okay? So I don't know whether it's going to be paid or not, but there will be Unity work, there will be VR work, with the Design Hub, and Carol knows quite a bit about the 3D stuff, right?
Yeah. So I just walked in. There's an internship over the summer.
Well, okay. Randy just talked to me yesterday. Okay,
Yeah.
this is typical of Randy, right? He just walks up and go like, "Tech, we need people. We need people like soon. We need people for the summer," because there are a few departments on campus, including EMT and some of the other allied, they call it allied health departments. They want They want to have simulations. So imagine you're with EMT. Okay, you're training emergency medical technicians, and you have these dummies that you have to purchase for. They're really expensive. Okay, so you want people to go through VR training first. Okay, so you might say, okay, EMT, VR training, how does that work? So you have this person laying down, the person is not conscious, right? So in VR space, at least the technician or the trainee can point at certain places of that person and go like, okay, this is where I'm gonna, measure the pulse first. Okay, this is where I'm gonna touch or check for breath, and stuff like that. Or is that person the first thing is I'm gonna put in or this person into a stretcher without checking first. So there are certain things you can do in VR, that is about following procedure. It's about doing the proper thing that can be trained and also be checked and tested in VR before you actually get that person onto an actual CPR dummy, where it can actually measure how much force you're applying to the dummy. So that's getting big. Okay, this campus is gearing up for a lot of VR training. The content is the problem. VR headset is not that expensive anymore, so departments can purchase VR headsets, and the gear, but to get the training content, from outside, is very costly. We are talking about $80,000 to start with. Okay. So the Design Hub is trying to gear up, to get enough people, to help write all of these code. Okay, some people will be doing 3D modeling, rigging, animation, and then other people will be doing the actual coding, so that we can actually write the programs to evaluate an EMT and ask, okay, did the EMT do the right thing? Given that this is the situation. So if you're interested, let Randy know. Okay, Randy Schuster. He's over at the Design Hub, Tech at 311. Okay, it's not going to start anytime soon, so we are talking about the summer, so you can still kind of think about it. If you have always wanted to learn about game programming, VR programming, and Unity, this is your chance, okay, to actually do something and actually get the get the guidance of people who have done it for some time. Yep.
So what are the odds of this actually being paid?
I do not know.
No idea.
The money thing is kind of, I do not know about the money thing, with the design hub.
Right.
But knowing Randy, he's going to try to get the money to pay our student interns. So it's going to be, what, $12 an hour or something like that. It's going to be
Minimum wage is
close to minimum wage.
Yeah.
Oh, okay. I'm getting things all mixed up. But it is still, if it is paid, it's actually not bad, okay, because it's on campus, okay. If you're taking a summer class, such as Cisp 310, which I'm teaching over the summer, so in the morning, you take Cisp 310, in the afternoon, you go to the design hub and you do your 3D stuff, your VR stuff and whatnot. Hey, that's not a bad, it's not a bad arrangement, right? Because you don't have to drive off campus to earn, well, it's still minimum wage, but you don't have to go anywhere else. You don't have a lot of overhead to get to your job. So if anyone is interested, just think about it. There are no process to register or to, sign up yet, okay? But you might want to think about it, to see if this summer you have time to do something like that. All right? Are we good? Yep.
This is a totally unrelated question to that, but you posted like a video of engineering types or something.
Yeah, I did.
I tried it, but every time I tried it, it kept on swapping between two different personalities.
Oh, you mean the MBTI?
Yeah.
So it depends on, how close those twos are. So, if,
It was executive and commander. Apparently, I'm ruthless.
okay.
But
So-
when an executive, or I think executive.
So
that one is
EST
passionate, so I don't understand how it switches between them.
Well, okay, I'm not going to get into the details of, how people can switch. And sometimes, the switch seems to be kind of like a lot, but it's actually not a whole lot. I think it all depends on how you answer the questions, okay? Because, objectively speaking, your MBTI type, depends on how you answer the questions, right? But some of the questions are not very clear of in which context are you trying to express your preferences. I'll give you an example, okay? So one of the questions it will ask is, in a group setting, there are multiple people, okay? And they're talking about something, people were expressing opinions. And you think other people are wrong. So the question is, will you try to preserve the group harmony and just kind of not say your disagreement? Or do you think truth is more important and you say, no, you guys are all wrong, and here's why? So that's one of the questions, right? So depending on your mindset on that particular day, or what just happened, or what may happen in the near future, you might put the context in a class setting. You might put the context in a family setting. You might put the context in a, it's just buddies and me getting together, kind of setting. So depending on the different settings, some people have different answers. Do you see what I mean?
Yeah.
So in the family setting, some people may say, okay, I'm just going to preserve the harmony, and you're assuming the topic is not important. Okay, it's about, are these apples sweeter than those apples in general? It's like, who cares, right? Yeah, you guys can I can disagree with you guys and I don't have to express it. But when you're at work, and it is about programming, it's about whether the program is ready to ship or not, and you found a bug, okay, and you say, no, this is a critical bug, we cannot release the program yet at this point. It is your obligation to voice your opinion and disagree with the group and say, no, I don't think we are ready to ship the product. So depending on the context, you can have an entirely different answer. And I think that's why you got different answers or different types as a result, because you put yourself in a different context when you try to answer those questions.
It makes sense. Because it just kept on switching. Like the first time I had commander,
Uh-huh.
times after that I got executive, and then after that.
So you're switching between ENTJ and ESTJ.
Yeah.
Yeah,
So I guess it's intuition and observation then.
correct. But those two can switch relatively easily, because if you go to 16personalities.com, they give you a numerical value, with each one. So if you're only 55% N, that means, just a very slight change of your answers will push you over to the S, and vice versa. Does that make sense?
Yeah, that makes a lot more sense actually.
Yeah, so it's not uncommon that some people may switch, types with only a difference of one single letter. It can be S versus N, T versus F. It's more unusual that people will have multiple letters to switch at the same time.
I switch between introvert and extrovert, and then thinking and judging.
Okay, so E versus I is entirely possible. Right, or you are very close, right at the border. So that means, depending on what you feel on that particular day, maybe you feel that you're really tired that day and you really want to kind of rest by yourself, then your answers may kind of lean more on the introverted side. Or maybe you have been introverted for a few days, okay, and you go like, I would like to talk to someone. Okay, so on that day you'll be leaning on the, huh?
The context in which you're thinking about everything matters.
Yep.
Because I get different scores based on what I'm thinking about at the time.
Yep. And then the P and the J can switch too. And once again, that depends on, to what are you judging, right? So with all that stuff, take it with a grain of salt. I can give you guys another website where it will give you the test and also give you the 4-letter code, but it will also give you alternatives. Like, this is what we think the best match for you, but you also have an 80% match with this and a 75% match with that. So that will give you kind of like a more complete answer to where you stand when it comes to your personality. So I can give you those additional resources if you guys are interested. All right, so we'll go ahead and get started with a new topic today, and I forgot totally to release the relation homework assignment. So I'm going to release it today, and you have a week to work on it, but I totally forgot last time. All right. So we are starting a new topic today, which is propositional logic. So I'm not sure how many people got a chance to read about this particular module, because it's a really long module and it has a lot of stuff in it that do not seem to connect with each other, okay? So that's why it is super important to read ahead of me so that you are not new to the concepts. You just need to know the details, from the class in our discussion. So this is the module, okay? So we'll go ahead and start with the overview. I'm going to close the door if nobody objects. He's a regular. Somebody who has a lot of opinions to express.
And time.
Hmm?
A lot of time too.
A lot of time, yes. Apparently he has plenty of time. At least he's not parking his car with the doors open and then the door speakers blaring his favorite music. He used to do that a lot too. Yeah. All right. So propositional logic. Okay. So propositional logic itself predates computer science by maybe 1,500 years or so. Okay, at least. Okay. So propositional logic is nothing new, okay, but it's a system for deriving the truth. Yes, I believe so. I'm just double checking. Yep, we are streaming and the audio is good. I'm not clipping the mic. Everything seems pretty good with the meter. All right, so it predates computer science, okay. It's a very basic stuff. I think the Greeks came up with that, originally. So it's a mechanical system so that we can, quote unquote, find the truth based on propositions. Okay, so if you are given a bunch of stuff and say these are known to be true, okay, what other truth can you derive from the known truths. Okay, that's basically one of the purposes of propositional logic, is to have a system to work with that type of logic. Okay, so we'll take a closer look later on. From our perspective, why is it important to us in computer science? Okay, because I always want to know how does it relate to computer science before I get into the details. Okay, why do you guys think this is important to us, in computer science? Okay. Yep. Go ahead.
Because computers are very stupid and you need to tell them exactly what to do in a logical way.
Okay, that's programming. Okay, and yeah, go ahead.
And if you have a set of, an operator that follows all of those sets of rules, the results will be reliable every time.
Okay, so you want to be able to prove something, right? So instead of just throwing some test cases and say that, yeah, that seems to be true here, that seems to be true here, that seems to be true here, how can you know that this is true universally? Okay, so you have some kind of condition that seems to be true for, let's say, odd numbers. Okay, yep, seems to be true with 1, seems to be true with 3, 5, 7, and so on. Okay, when do you stop? Because it's always possible the next odd number would make that condition false, right? So how do you prove it conclusively and say that this is going to work for all odd numbers? Okay, once and for all, you don't have to use any test cases. Okay, so that's kind of why propositional logic or proofs in general is useful. Okay. So anyone else? Does anyone else want to kind of add to the discussion why propositional logic is important, or why logic is important in computer science in general? Why do we want to prove things? Because the whole idea of propositional logic is we have a mechanical method of proving theorems. Okay, that's kind of the whole gist of propositional logic. But why is that important? Why do we care about theorem proving when we are supposed to be just writing programs? What is a program? Program are instructions, right, for a computer to follow to do certain things, right? Can that be modeled mathematically? In other words, can we model the behavior of a program mathematically? Let me rephrase that question a little bit, okay? If I give you the precondition of the input into a program, I specify the exact steps in the program. Okay, you got loops, you got conditional statements, okay, you got expressions, we got assignment statements, and so on and so forth. And can we prove at the very end of the execution of that program that these conditions must be met if the program is to execute? We would like that, don't we? Because this way we can prove that a program works 100% all the time. What if I throw something that is intentionally erroneous into the system? The proof sets, it will ignore that. Okay, it will basically ignore that and report back, this is erroneous, no processing is done. Okay, instead of trying to process it and causing security issues to happen. So this is why it is important for us to prove the correctness of programs. Propositional logic is not quite powerful enough to do that, but it does help us understand what is involved in theorem proving, but in a mechanical way. So this is kind of like the introduction to mechanical theorem proving. Okay, it just gets you thinking in that direction. So what we'll do now is to go talk about what is propositional logic. So when we talk about propositional logic or the calculus, it is a system that is a 4-tuple. Okay, so the 4-tuple has, okay, let me zoom in, has 4 Greek letters. Okay, so these are all Greek letters here. So what looks like A is alpha, omega we all know, this is zeta, and then that's iota. Okay, but if you want to call those like A, omega, Z, and I, it's fine. Okay, I'm not really picky about terms in this class as long as we know what it is. Okay, as long as the context makes it clear what we are talking about. So with this for tuple, each item in the for tuple being a set itself, we describe a propositional logic system, okay, a calculus. So now we look into each one and try to find out, okay, what exactly is it? Alpha is the set of symbols that we'll be using, and symbols have no inherent meanings in this case. So what symbols are we talking about? Okay, there's a little discussion later on, but I'm going to fast forward just a little bit to talk about what symbols we are talking about. So you have symbols to represent constants. Okay, so in this class and also in Cisp 310, I use 0 to represent false. I use 1 to represent true. And then we have what we call variables. Okay, so variables are exactly what the term means. Okay, each letter A, B, C, or usually we use P, Q, R, S, T. Okay, so we can choose P, Q, R, S, T as our variables. And the term variable versus constant is something that you are familiar already. So when we use P, Q, R, S, T or something like that, it simply means that, well, it can be true or false. We don't really know ahead of time whether it's true or false. Okay, as opposed to 0 or 1 is a constant. Okay, they have fixed values already, and then P, Q, R, S, T do not have fixed values. They can change. Okay, and then there's another group of symbols that I will talk about later. They're called schematas, and why we need those things, we'll talk about those later. Okay, so we are only talking about, in other words, in programming. Okay, if you think about C programming, alpha is really just talking about what digits can you use for numbers. Okay, what can you put into an identifier? Oh, okay, an identifier can have lowercase, uppercase letters, the underscore, and digits as long as it is not the first thing. So we are talking about the most basic components, when we talk about alpha. Omega is a set of operators. So you can see operators as connectors. Okay, all they do, okay, is to say, give me an expression here, give me an expression here, and this is an operator that can operate on those two values. Okay, but it's generalized, which means an operator in the omega can take 0, 1, 2, or any number of operands, okay, in general. But the propositional system that we're going to work with in this class is going to be much more restrictive, and we'll talk about that later. But omega are operators, okay? That is the set of operators. So give you a context of what operators we are talking about. Logical AND is an operator. Logical OR is an operator. Logical NOT is an operator. Implication is an operator. If and only if is an operator. So those are the operators that we have used in this class, and that's basically what operators are. Are we good so far? Okay. The next one is zeta, okay, or z. This is a set of what we call transformation rules, or we call it productions, okay? So each transformation rule is also known as a production. So these things are really cool, okay? Because what they can do is they can take one expression that meets a certain format or requirement or syntax or just the structure, and transform that into a different one. Is that okay? So this is how we can derive things, okay? We start with this, and they match a certain pattern. Then we say, oh, if we have this and we have this already, and they match a certain pattern, then we can derive that. Is that okay? So that's what transformations are. And then the last one is iota, okay? Iota or I is a set of what we call well-formed formulae, which we'll talk about later, that are known to be true. Okay, so iota is what gives quote-unquote meaning to a propositional logic system. Okay, it provides the semantics to the entire system. Without the iota, okay, well, there's not a whole lot to talk about. There's not a whole lot to do because we don't know what is true to begin with. Okay, so iota gives you the seeds of what is known to be true. And then using the rules in zeta, we can try to derive more and more and more truth as results of what is known to be true in iota. And hopefully at some point, we can prove a particular expression that you're interested in is true. Are we doing okay so far with these symbols and the context? Okay, so what letters, what is the basic alphabet? What are the operators or connectors or punctuations, if you will? How do we transform basic sentences? If this is true and that is true, oh, by the way, that has to be true too. That's zeta. And then iota is, so what do we know is true to begin with? Okay, yep.
So in zeta, would we have like De Morgan's law?
Yes, so zeta would have, okay, so it depends on what you want to work with, but a human-friendly propositional system would have De Morgan's law, it would have the distributive law, it would have the factoring rules, blah 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 blah, commutative rule, right? So associative rule, those will all be encoded into zeta. Okay, so that's a good point to make. Are we doing okay so far with this discussion? Are there any questions, any comments? All right, so if there are no questions, we're going to move on a little bit. So one of the key concepts is what we call a well-formed formula. Okay, it is a WFF, not a WTF. So a WFF, or well-formed formula, is defined as such. Okay, so there's a lot of symbols already here. Okay, so I'm going to go a little bit slower. Okay, just so that we can get familiarized with all of these symbols and all the expressions and what they mean. So this is true. Okay, for all E in alpha is a WFF parentheses E is true. In other words, if you take any symbols out of the set alpha, each symbol by itself is by definition a well-formed formula. Okay, so true by itself, 1 is a well-formed formula. 0, or false, is a well-formed formula. P as a variable is a well-formed formula. So it's Q, R, S, T, and so on. Is that okay? So this is the building block. Okay, this is the most basic building block of a well-formed formula. So are we good with this particular statement or this particular expression? So I'm using is a WFF as a predicate or as a function. When it returns true, then whatever is the parameter, in this case E, is a well-formed formula. So it's just a shorthand of what is a well-formed formula. Is that okay? Sort of?
What does it mean to be a well-formed? It kind of begs the question.
So this is how we define what a well-formed formula is. So if you take any symbol by itself out of alpha, that symbol is by definition a well-formed formula to begin with. It's the most basic and the smallest well-formed formula you can have. It's just a symbol that you choose out of the set alpha. Okay, so if your alpha has 0, 1, p, q, r, s, t, then individually 0 is well-formed, 1 is well-formed, Q is well-formed, R is well-formed, S is well-formed, P is well-formed, T is well-formed.
Because they're unambiguous?
Nope, because that's the definition. So that's just the definition. Okay, everything in alpha by itself is well-formed. Okay, so we are just talking about the syntax. Okay, we're asking what is going to throw a syntax error. That's basically what we're asking. The second rule is nasty. Okay, it's just gnarly to look at. Okay, and that's intentional because I want you guys to get familiar with this type of notation. Okay, because when you move on to a 4-year university, you might encounter a class that also makes use of mathematical symbols, not unlike this. Okay, so we'll read this carefully, just step by step, and see if we can get it. Okay. So for all I in 1 to n, okay, so we have to find out what n is. Well, we have, so n is used in here, okay? So omega n is basically a subset of omega where all the operators in omega n has n operands. Now that concept is kind of foreign to us, Because when we think about operators like and, or, not, and so on, either it is a binary operator or is a unary operator, right? So that means as far as operators that we are familiar with, they are in omega 2 for binary operators or in omega 1 for unary operators. And is a binary operator, or is a binary operator, implies is a binary operator, if and only if is a binary operator, and then negation is a unary operator. Are we doing okay so far? So most of the time we do not use a whole lot of operators that require more than 2 operands, okay? But in general, that can happen. Okay, so that's basically what omega n is representing is, well, in case we have operators that take more than 2 operands, we know how to express that. Okay, so as far as you're concerned, you can just kind of say I can only be 1 or 2. Okay. So given that I is 1 or 2, is a well-formed formula. This is phi of I, and C is in omega, omega n. I'm just looking at this. Okay, so n is so n is fixed to, so we're only talking about omega n. In other words, we're only talking about a particular omega in this case. So if you have identified components, okay, so phi of I are components that you're feeding to the operator. Are we good so far? So just fix n equals to 2 for now, okay? Just whenever you see n, just say it's 2. So that means and I is, in the set of 1 to n, so I can either be a 1 or a 2. So that means phi of 1 is a well-formed formula, and phi of 2 is also a well-formed formula. Are we good so far? And C as an operator is in omega of 2, which means it's an operator that takes 2 values. That implies when you apply the connector or the operator that is binary on just phi 1 and phi 2, this expression is also well-formed. Okay? It's just a very gnarly way to describe it because I want to make it so that it can also describe operators that require more than 2 operators. Okay, so let's use some examples here because I think this is a good time to think about some examples. So we go to mousepad, and I think we can do most of the things in mousepad in this case. So we'll say alpha is 0, 1. Those 2 are constants. P, Q, R, S, T. If you want more variables, it's okay, but most of the time, for examples, 5 variables is plenty, okay? And then we specify omega, okay? So we say omega 1 only has negation. So we'll just say exclamation point for negation. And then we'll say omega 2 has the usual operators that we are familiar with. So it has and, it has or, okay? We'll just say those 2, okay? For this example, we are limiting ourselves to just, and or, okay? Because, it's just an example. All right, so this is all I need in order to define what is well-formed, okay? So 0 is a well-formed formula. How do we know? Because it's by definition. Okay, you take any symbol out of alpha by itself is already well-formed. Okay, that's by definition. Okay, so if you want, you can say, oh, R is a well-formed formula. Okay, T is a well-formed formula. All that means is it does not violate any syntactical rules. Okay, it is syntactically okay. Structurally, it is okay. Well, is it true or false? I don't know. So far, we have not assigned any semantics to these symbols. Are we good so far? Okay. Then we move on to the application of these symbols. Okay. So we'll use the usual way of applying negation, which is a prefix. So we say not R is a well-formed formula. Well, is it well formed? Well, let's double check. How many operands is negation expecting? One. Did I supply exactly one operator? I mean, one value for it to operate on? Yeah. So it's now well formed. Okay. Let's check out some other stuff. Okay. So we'll say, what about N and Q? Okay. Is that well formed? It is not well formed because AND requires two values to work on, and I'm only supplying one, so it is not well formed. Okay, so we'll say this is not a well formed formula. Okay, so let's do something that's more complex. Okay, so we'll do a Q or P and T. Is that well formed? Well, wait, hold on a second here. That has nested operators and whatnot. How do we get this to work? You do it recursively, okay? The last operator is the OR, okay? So you say, we'll determine whether the OR is okay or not once we have determined the two sides or the two values that we are feeding to the OR. Is that okay? So the first thing we look is Q, which is on the left-hand side of the top operator, and you ask, is Q by itself a well-formed formula, and why? It is, and why is that the case? It's by definition, okay? Because you can find Q in alpha, and as a result, it is well-formed by definition. Yes?
So what's preventing you from putting like a plus sign in A, and then trying to use that?
A plus sign in A?
Yeah.
Because in that case, then the plus, you can do that if you want to, but if you put plus in A, then plus is no longer an operator. It is now considered a variable or constant. Now, whether it is a variable or constant depends on the semantics, depends on iota. Okay? All right, so now that we know Q is well formed, then the next question is, what about the other thing that I'm feeding to the OR? Is that well formed? So now we are focusing on P and T, and the question is that well formed? So we focus on the P and the T first, right? Because those two are the most basic level stuff that we are feeding to the AND. And we say, yep, P is in alpha. It is by definition well formed. T is the same way. It is in alpha. It is also well formed. Are we good so far? So if you provide exactly two values to an operator that requires two values, then the entire expression is also well formed. Is that okay? So now we know that Q is well formed. We know P and T is also well formed. So they provide exactly the two values that I need for OR. So that means the OR is also well formed. Is that okay? So you have to analyze, an expression sort of recursively to know whether it is well formed or not. Now, something being well formed doesn't mean it is meaningful. Okay? Doesn't mean it's actually useful in any way. I'll give you several examples. Okay? So, do you think this is well formed? I can find Q in alpha, right? And I'm supplying exactly two well-formed formulae to AND, and as a result, the AND expression itself is also well-formed. Okay? What about this? And since I'm limiting to binary operators, I'll make sure that we structure our expressions exactly like that. Is that well-formed? Okay. And you can see how I can keep going like this. Q and Q and Q and Q and Q and Q indefinitely, and all of those are well formed. Well, is it useful? I don't know. I mean, I don't know what we are trying to prove, but they're all well formed. Syntactically, they're fine. Are we good so far? Okay. So well-formed formula is really just providing the structure of the expressions that we can process in the propositional logic system. Is that okay? Yep.
With our examples in the parentheses,
Mm-hmm.
to be a well-formed formula, just to be clear, they both need to be well-formed formulas within the parentheses for the entire thing to be
Correct. So the reason why I put in the extra parentheses is because and is only taking 2 operands. So I have to make it clear that this one is taking the entire left-hand side, as one single value, and is taking q as a single value on the right-hand side to make this particular the top level AND expression. Yep.
We don't need parentheses in Omega?
No, because the parentheses are only here because we are used to infix notation. Okay, so
Otherwise, we write it in postfix.
yeah, so the meaning of the operator has nothing to do with the notation. So the notation of choosing infix is simply because I think most people understand infix more so than the other 2 alternatives to express to deal with expressions. Okay. And I'm waiting for someone to say, what are the other 2 ways of expressing expressions?
Infix and postfix are done.
Tack, what are the other 2?
Oh, I'm so glad you asked. We got a special today, and I'm going to give this to you for free. All right. So besides infix notation, okay, so infix refers to where is the operator relative to the values that that it is supposed to operate on. Okay, so infix basically is saying, oh, it is between the 2 things that I'm supposed to operate. Okay, so that's why we call it infix notation. We have been poisoned by the infix notation ever since we got to, I guess, elementary school. Okay, I'm guessing by 1st grade we will start to understand what is addition, right? So we have been poisoned for decades, and that's why we are used to it, and we don't feel it's poison anymore. But it's actually a very bad system. Okay. Okay. So now the question is, what are the alternatives? Okay. So let me just use an example. Okay. P and Q, or T, and we take a negation of the whole thing, and then we'll say S or this entire thing. Okay, so this is using infix notation. Some of the parentheses may be avoidable, like the one around the end, because we can define priorities, right? Some of these parentheses cannot be avoided. The negation, the parentheses to the right-hand side of the negation cannot be avoided because I want the negation to apply to the result of the OR, not to P. So we cannot avoid that negation, that pair of parentheses. So the question now is, so what are the other 2? Well, one is called prefix. The other one is called postfix. Okay, so there's prefix and there's postfix. We'll deal with the one that you are also somewhat familiar with, which is the prefix form. Okay, the prefix notation is something that you're actually familiar with because that's how we pass arguments to functions. You spell out the name of the function first, and then you provide a list of values as arguments so that the function can operate. Does that make sense? So all we have to do now is to look at each operator as a function, and then that will give you the idea of how to express this thing using the prefix notation, which also needs to use a lot of parentheses, okay? But it's no longer limited to only 2 things. Because infix, as the name implies, is the operator is between the 2 values, right? So you can't really have 3 or 4 values easily, when you have an infix notation. Okay, so to make this, turn this into a prefix notation, the OR is the last operation to perform, so it is on the outermost portion of the entire thing. Does that make sense? Okay, so we have the OR, and then inside the OR, now, so don't copy me because I'm doing it in a structural way. So I just say, okay, we need 2 things for the OR, and I leave the space here and have a comma to separate those 2. So now I have 2 slots to specify the 2 values that I'm supposed to OR in this operation. Is that okay? So the first thing I need to OR is whatever is to the left-hand side. That's an easy one. Okay, it's just variable s on this side, and then on the other side we got this thing here, right? So I'm going to work on this step by step so that we don't skip any steps. So we now have a mixture of infix and prefix notation. So I'm gonna fix this like one thing at a time. All right. So when you look at this negation, negation is pretty easy because negation only has one single operand or one value that it's supposed to work on. So it's already in prefix notation. Okay, there's no infix version of negation. So it's already done, so we can just remove this parenthesis, and let me just double check. I think, oh, I might have missed one to begin with.
You do.
Huh? Yeah, so there's an extra one, I think, all the way over here. Okay, so negation is easy because now we just say, oh, the negation has one single operand, which is this portion. Now that is still in infix notation. I'll fix it, in a while. Are we doing okay so far? So now we take this and we say, okay, let's go ahead and move and fix more things. So now we have a OR with P and Q as one thing is ORing, and then T as the other thing is ORing. Is that okay? And now we take this and we say, okay, we only got one more step to go. The AND has P and Q in it. So now the whole thing is now turned into a prefix notation. So prefix notation is not foreign to you because we already know how to call functions or call subroutines in C, C++. Most modern programming languages use this notation to supply arguments when you call a function. So we should be pretty familiar with this concept already. The only thing that is strange about this is bar cannot be used as a name of a function in C or C++. Okay, but I'm just borrowing that as a symbol that we have used earlier. So it's not that big of a deal. Are we still good so far? Okay. So the weird one that we have not talked about is the postfix notation. Okay. So postfix notation, as the name implies, means you supply the values first, then you tell what to do with the values last. Okay. So that one is really weird, or weird to most people when they first encounter it. But the more you use it, the more it makes sense. Okay. So the way we work on that, okay, let me see if I can express the thought pattern to convert from infix notation to postfix notation, okay? So we'll take the infix notation again because I want to work on this somewhat step by step, okay? All right, so we put it here, and then the first thing we ask is, what is the last operation that we need to perform? It's the OR, right? So we supply the value S, and then somehow we supply the value of the right-hand side of the original OR, and then we say, hey, now you got two values, give me the logical OR of those two values, okay? So the way we express that is we just take this and move it over here. So now we have a mixture of the postfix notation, and we still have a whole bunch of this, in infix notation. So now we go in here, okay, and we ask, we can work on this step by step, okay, so this is P and Q. So what we can do here is we say, oh, okay, in in postfix notation is PQ and. You specify the values first, and then what you want to do with the value. So when you have PQ and, it gives you a single value back, which is the AND between the P and Q. So that gives you a value back. What we want to do with PQ AND is I want to OR the value of P and Q with T. So the way we do that is we specify T, and then we say OR those two together. So that takes care of this part here. And then we have the negation. So the negation, which is all the way over here, applies to the result of, okay, look up the original expression here. What is the negation applied to? It applies to the result of the OR. So that means when we do the conversion, this is the last operation to perform after the OR. And now we have the whole thing done. We just have to remove all the parentheses because they are no longer needed. This is the postfix notation of the original infix notation. And you can see how it does not need parentheses. right? And it gets the same job done. So I'm not going to test you guys on how to convert infix notation to postfix notation, okay? But the question is, the begging question in your mind is, is it really helpful to learn about postfix notation? Why would I be interested in postfix notation? So the answer to that question is context sensitive, okay? Now remember that phrase, context sensitive, because you will hear that again in a four-year university in an upper division class called automata theory or computational theory, okay? Now, who came up with those terms? Context sensitive, context free? Well, ask Alan Turing. He's the guy who came up with those terms. Okay, but anyway, in this context, why do we want to be aware of postfix notation? I mean, obviously, it's not something that we are taught, okay? It is not something that you use in a regular programming language, okay? So why do we want to know about postfix notation? Now, if you ask an engineer in his or her, 60 or 70, okay, that person will tell you, hey, the calculator that I grew up with, and also that I use at work, those original HP calculators, they only understand postfix notation. They don't understand infix notation at all, okay? They can only understand postfix notation. So on your fancy TI calculator, okay, you can use parentheses. You can say, 1 plus 2 in parentheses times 3, and then specify the actual value that you want to compute, right? The engineers, in the 60s, 70s, at least, possibly in the 80s, and going into the early 90s, they all have to convert everything into postfix notation before they enter the expression onto the calculator. Then you might ask, why? Well, it's because the calculators back in that time did not have a whole lot of processing capability. Parsing parentheses takes quite a bit of programming. But this postfix notation does not require any processing of parentheses. It makes the parsing a whole lot easier when you use postfix notation. Are we good? Okay. And somebody may ask, well, we don't really care about historical relics. Okay. In fact, you can download RealCalc, okay, RealCalc, okay, which is an app, an Android app. The calculator has a RPN mode, okay. RPM stands for reversed Polish notation, which is a fancy word or fancy phrase to refer to the same thing, postfix notation. Okay, so old engineers can actually download an app onto their latest and greatest cell phone so they can continue to use postfix notation because they're used to it, or for nostalgic reasons. Okay, but those are not very good reasons for you to learn something, right? Okay, so why do we want to learn something like this? Has anyone looked into a PDF file and find out what is inside a PDF file? Oh, by the way, what is PDF? Portable document format, okay? And what does it do? How is it different from a PNG? If I were to produce something, okay, from, let's say, word processing software, okay, if I can choose to produce a PNG or GIF, or JPEG versus a PDF, which one is usually considered a better option? You can edit the text later, but there are other reasons why the PDF is better. If you want to print, yeah, go ahead. You can search, okay, but there's a little bit more to it. When you zoom in, to a PDF, and you keep zooming in and zooming in because there's a picture with some details, or the equation has tiny little fonts, and you have to zoom in order to see, the equation or the subscripts and whatnot. What happens when you have a proper PDF as you zoom in? It scales just fine. Everything looks smooth, right? Okay. In fact, the effect we can see here, because I use math jacks So you can see how I can zoom in and the math equations still look pretty good, okay? And that's because in a PDF, it is not a bitmap. Unlike a PNG, which is a raster representation of stuff, if you zoom in a raster, what do you see? You see bigger pixels, right? So you see the rasterization of all of these things, and things are not smooth anymore. So that means if you want to produce a PNG, okay, from a Word document, you kind of have to think about, well, if I want to print this out, what is the resolution of the printer that I want to print it on? So you can say, well, the best printer I have is 1200 dpi, okay, dots per inch. But a lot of printers don't have 1200 dpi, so when you print to 1200 dpi, you're going to use up a lot of space that you really do not need to. Does it make sense? And if you want to blow it up to be a billboard, thing, well, guess what? You'll see rasterization again. Okay, that kind of sucks. But PDF says, well, let's not do this, okay? Instead, we'll describe how to write a letter A. Okay, what are the curves? Where's the straight line? Where do we start? Where do we end? How much curve are we talking about? That's what a PDF is describing in itself. Okay, now it does have a font concept, but for pictures, diagrams, and plots like that, it actually describes how to draw the lines. Now, if you describe how to draw the lines, and you have a low resolution device like the projector here, well, it's still not going to look very good, but that's a device issue. But if you say, oh, I got this really nice printer that can print to poster size, okay, and you describe how to draw those lines, it's going to draw those lines at the resolution of the printer, so everything looks super smooth. Does that make sense? So now the question is, how do we specify to draw a circle over here? Well, we have to specify the center. We have to specify the radius, right? Possibly the thickness of the line, okay, and so on and so forth. And what does this have anything to do with postfix notation? In the PDF, when you want to draw a circle, you specify x, y, radius, and then you say draw circle. You specify all the values first, then you specify what to do with the values that you have specified. So if you look into a PDF, that is what you get. Okay? But why? Why does the PDF use this instead of infix notation so I can read it more readily? Because infix notation requires a more complex parser. Postfix notation, easy peasy. Okay? You just need a stack and just be able to scan through the symbols. You're good. Yep.
So is that why CAD and like SolidWorks sometimes use that as well?
Yes. Yep. Yep.
I was always wondering about that.
And that is also why in CISP 310, my assembler also takes postfix notation, because I was too lazy to write a parser that can do infix notation. You can make a converter. There are converters on the internet that can do that. Okay, so this is kind of a big digression to the representation of operators, which is irrelevant to us, okay? Because all we do is we take a operator out of omega 2, and we just say, okay, we are expecting two values to use this particular operator. That's all that matters to us, okay? What it looks like, how we represent it, is not really that important. All right, so kind of like a big digression here. But you can see how this particular rule is going to recursively define bigger and bigger and bigger well-formed formulae. Does that make sense? Are we good so far? Okay. All right. So at this point, we know what the symbols are. We know structurally what is a valid expression, that it is syntactically correct. So what do we do with all of these well-formed formulae that we can span from alpha and omega? So we move on to iota at this point. So iota is a set of well-formed formulae that are known to be true. Okay? Then you might ask, okay, what does that mean, known to be true? So I'll give you an example. So we'll expand our example in mousepad. And I'm going to go all the way back to here. So we now define iota. So in iota, I can define 1 in here. Because remember, every expression, every well-formed formula in iota is known to be true. This is how I define 1 to be truth itself. Because it is a constant in iota. Every expression or every well-formed formula in iota is known to be true. 1 is known to be true. So that defines what true is. Does it make sense? Then you might say, well, then how do we define false? The negation symbol applied to 0. Okay? So these are constants. Okay? This is how I define the constant true and how I define the constant false. What about the variables? Okay? So the thing is, you don't want to define p to be true because that means p is just a constant of true, which means it's not exactly a variable. So the variables come in handy when you can say something like this. So you can say p or q as a well-formed formula is known to be true. Then you go like, but that doesn't tell us anything about p or q themselves, right? We just know that at least one of those two is true, but which one is true? Which one is not true potentially? Doesn't tell you anything about that. Is that okay? You can also have other things such as S and not T or P, okay? So you can make these well-formed formula, fairly complex, okay? But at the end of the day, all we are doing is simply to say what well-formed formula or what well-formed formulae are known to be true. That is what iota is saying. Is that okay? But it gives meaning to the entire system. Because without iota, all you have are symbols and expressions that are known to be grammatically correct. But there are no meanings whatsoever associated with those expressions. They're syntactically correct, but is it true or not? We don't know. This gives you the starting point of, well, we know these things to be true to begin with. Are we okay so far? Yes? Okay? So at this point, I think it's good to have a mental picture of what we are trying to do. So if you imagine a space, okay, so once again, we are using the concept of a space, okay, and this time it's not a two-dimensional space. I'm just using, a two-dimensional representation so that we can do something about it, okay? So there's a space, and in the space we have an infinite number of points, okay? I'm looking for another color, and yep, there's one here, but I'm thinking maybe I should use my Zerno to do it. Yeah, so I'm going to switch to the Zerno so that it's recorded. Okay, there we go. All right, because now I can use any color I want. So we go to page, and I'm going to change the page style to just plain. There we go. And I'm going to say that every single pixel of this space is representing a well-formed formula. So that means there are a lot of well-formed formulae in this entire space. Is that okay? Because we already know how to combine operators with the result of other operators to make longer and longer and longer, but not necessarily interesting expressions. Is that okay? So what we are doing with iota, okay, in red, is iota defines certain points in this space, and it says, yep, these things are known to be true. Okay, that's what iota is doing. Okay, it's just labeling certain pixels in this entire space and say, yep, these things are known to be true, don't ask me why. Is that okay? So now you say, well, I'm interested in one thing, okay? I'm interested in this green pixel over here, and I want to know whether that is true also. Okay? So the green pixel over here is also a well-formed formula. It is not in iota. But I want to know, is this green pixel also true? Given that we start with the red dot, knowing that those are true, do we know whether the green dot is true also? That's your proof, okay? This is what we want to prove. So now the question is, how do we get there? The transformation rules in Zeta is what we use to do this, okay? So Zeta is basically saying we can do pattern matching, okay? And if we say that, oh, this one and this one, together match the prerequisite of a production. So knowing these two things, we can now say that this thing here also has to be true. That blue dot was not in iota. It was derived from two things that are actually in iota. Is that okay? So the blue line or the arrows is indicating the application of a production rule. Is that okay? So now you say, oh, okay, we got a few other production rules too. So we can go from this one to this blue dot over here. We can go from this one to this blue dot over here. And, oh, by the way, these two, they match a particular pattern. So together, they can give me a blue dot over here. So I'm starting to label dots of this entire space to be, yeah, these things are now known to be true because they can be derived from the red dots. But nobody's going to stop you from taking two blue dots or one blue dot and transform that or use that to label another blue dot. Okay? So now we can say, oh, now I can use the results. Okay? I can take this blue dot over here, and I can take this blue dot over here and label this dot also to be blue. Is that okay? So now we are starting to look at this and go like, oh, here's another blue dot. But you know what? This blue dot over here and this blue dot over here can also label that dot as blue. And then this combined with that can label this dot to be blue. And this dot being blue is now saying that, oh, by the way, this one is blue as well. Now I have proven that this dot, which was my objective, I want to know whether it is true or not. Now I can draw blue arrows from the red dots to connect everything to the one that is circled in green. Is that okay? Does everybody see how each item in the 4 tuple is represented in this picture? Alpha is not represented too much because each pixel is already a well-formed formula. So when you look at each pixel, it consists of operators and things from alpha. Okay? The red dots are the ones in iota. These are the well-formed formulae that are known to be true. Okay? And don't ask why, they're just given to you and say that you can assume these things to be true. The blue lines, the arrows, are indicating the application of productions in Zeta. Now, you can apply applications after applications. If you can get to, and then the dot that is circled in green is the theorem that you want to prove. Okay? So now the question is, okay, can we find a way to reach the dot that is circled in green using the blue arrows? That is the whole question of theorem proving. Is that okay? All right? But the problem, there are a few problems with this approach, okay? Because using the algebra system that you guys are familiar with, including Boolean algebra, you can have productions that will give you results that are not really particularly helpful, okay? I'll give you a few productions that are seemingly not very helpful, okay? So one production, looks like this. It says true implies, okay, I should not use imply, so I can't write that symbol, which is a T rotated, uppercase T rotated counterclockwise 90 degrees. Okay, so there's no way for me to enter that over here. So I would just say, I infers, okay? I think it's infer. I have to look up my document. So I'm going to use a special symbol here to represent it. So I'm going to use this kind of special symbol here to represent, it can transform to, okay? So it can transform to P or not P. Okay? Or I should say nothing. Okay? There's nothing on this side, not even true. So this transformation rule can say out of the blue, out of nothing. Okay? I don't even need a red dot to begin with. I can start to label a lot of blue dots now. Do you see what I mean? Because remember, the blue dots are representing things that are known to be true. This is a transformation rule that allows me to start with nothing and conclude that P or not P is true. Okay, that's logically valid, but is it helpful? Okay, maybe, maybe not. Other transformation rules can be a little bit more helpful. Okay, for instance, I can have not A or B and A, and then the transformation rule says if you can find these two, okay, this is not an and here, this is a comma, and the transformation rule says B. Okay, so let me explain what this transformation rule is saying. So the transformation rule is saying find me a well-formed formula such that the last operator is an or, but the last operator of the left-hand side is a not. Okay, that's the structure I'm looking for in one of the well-formed formulae. And then the second part is, oh, by the way, whatever you're negating on the left-hand side of the or, if that thing appear by itself, if I can find these two well-formed formulae, then label that B, okay? The well-formed formula that is B, which is the right-hand side of the or, label that one blue too. Are we doing okay so far with this transformation rule? Okay, so once again, let me describe, how to apply this particular transformation rule. Okay, you basically go through everything that is already labeled blue or labeled red to begin with. Okay, go through every single dot, and you ask the question: does it fit this particular, format? Is the last operator a or, and then whatever is to the left-hand side, the last operation is a not. Okay. So that's a pattern matching thing, right? You can just kind of go through all the dots and find out, yep, this one fits that requirement, this one fits that requirement, this thing fits that requirement. Okay. For each one that fits that requirement, then you ask, whatever I'm negating on the left-hand side of the or, is that thing also labeled blue or red? Is that okay? Are we doing okay so far? So if you can find something of this particular structure is already blue or red, and you find that the subcomponent that was inside this thing is also labeled red or blue, then you say, oh, now we can go ahead and label B as blue as well. That is how we apply a transformation rule. But the problem with this is you can have stupid transformation rules that will lead you nowhere. Okay, you'll be labeling more and more dots to be blue, but it's not going to be helpful. I'll show you an example. Okay, you can start with something like this: A transforms to A or A. Okay, so logically it makes sense, right? If a particular well-formed formula A is known to be true, okay, either it's labeled red or blue to begin with, then that well-formed formula or itself is going to be true as well. So logically, it makes sense. Okay, when you apply this particular transformation rule, you'll be labeling more and more and more dots to be blue. Is that okay? Do you think those blue dots will lead you to the theorem that you're trying to prove? Probably not. The second question, is there a natural end of how many times I can apply this transformation rule, so at least I'll hit a dead end and know that I have to turn around? No. So the problem is, okay, now this part is really important because it relates back to the rationale of what we'll be talking about next Monday, okay, is the space, okay, let me switch back to this representation here. The space of all well-formed formulae is infinitely large, okay? So the search space, your haystack, is infinitely large. The needle, which is the theorem that I want you to label blue, okay, may or may not be in the haystack. Okay, so imagine this problem, okay? I want you to find this needle in a haystack, okay? Simple problem. So if you have a small and finite haystack, you go like, yeah, tag, I'll be done in 5 minutes, okay? I can search through the whole thing and I can come back with an answer. Either, yes, the needle is in the haystack, or, well, Jack, you were trying to trick me. That needle is not in the haystack, okay? But I can conclude in 5 minutes because the space is small, right? So now I ask you and go like, okay, do the same thing, but with that haystack over there. But Tag, that's a huge haystack. Yeah, but it's still finite, okay? Okay, Tag, it might take me a few days, but I'll come back to you with an answer in a few days. So in a few days, you might come back and like, finally, I found your needle. Or you come back to me with a lot of negative emotion and go like, you tricked me. There's no needle in that haystack. All 10 cubic yards, no haystack over there. Okay, but it's still finite. Okay, you can estimate how much time it would take you to come back with an answer, right? So now I say, okay, do the same thing, but do it to that haystack over there. You look at that haystack and go like, there's no end to that haystack. It's an infinite haystack. And what I want you to do is to say, now, this is the needle that I'm trying to find, okay? It may or may not be in that haystack. Don't you think that's going to be a question that's a little bit difficult to answer? Because you don't know when to stop, okay? Just because you haven't found the needle yet is inconclusive, whether you just haven't found it yet or it is actually not in the haystack. Is that okay? So the case when the needle is not in the haystack is basically saying the thing that is circled in green is not a theorem. It is not a consequence of the red dots to begin with. Okay? If you find the needle, that means, yep, we have a way to prove that the pixel that is circled in green is in fact a consequence of whatever is initially known to be true. Is that okay? So the problem that we are having right now, remember this, for next Monday, is we have an infinitely large haystack, and your job is to come back with a conclusion of, yep, I found it, or at least you can tell me, no, I don't think it's in a haystack, and it's not a problem that you can solve when your haystack is infinitely large. So we're going to transform the problem space so that it is finite, so that we can actually come back with an answer. I mean, it might take a while, but we know how the worst case scenario once we transform the problem. So that's the whole purpose of CNF, or conjunctive normal form. So you might want to read up to resolution and conjunctive normal form in this module. All right. Have a nice weekend, and I will see you guys next Monday, and I'll open the homework as well.